Hello everyone. In this video, we will derive the equation for the hoop stress in case of a thin cylinder. So we know that in case of a thin cylinder, the thickness is less than d by 22. So in order to derive the equation, what we are going to do is we are going to take this thin cylinder and you know that some internal pressure is there because of some fluids passing through it, right? So because of that, hoop stress will generate inside of the wall, and it is responsible for hooping the walls outward. As you can see, it's bursting, it's just going outwards, it's hooped outward. So why is this happening? We'll understand that. So here I have defined some things like these stresses that you can see, the tangential stresses, these stresses I'm talking about, these stresses, they are they are sigma h. Sigma h is my hoop stress. Because of this stress, because of this hoop stress, what is happening here? The walls of the cylinder are hooping outwards, right? So what I'm going to do is now take a look at this red marked region. Okay, this region that I have just colored with red. So this is the thickness, this is the thickness T. Okay, this is the thickness T. Here you can see I have marked it T. So because of this is the thickness. Okay, I have got this, and the internal diameter, that is small d. Okay, so now what I'm going to do is I'm going to find the hoop stress, right? I'm going to find the hoop stress. So hoop stress is also named as circumferential stress, and you know that stress is force over cross-sectional area. This is the general derivation or definition for stress. You know that stress is going to be your force upon cross-sectional area. So for hoop stress, this is also the same, right? Now I need to figure out the amount of force. Okay, so in order to find the force, what I can use is, I know that force is equals to pressure into area, because from the definition of pressure, we know that from the definition of pressure, pressure is force upon a unit area, force upon any unit area. So this is the definition for pressure. So from here I can write that for in case of force equals to pressure times area. So here pressure is P. This pressure is due to the fluids passing by it, right? And here I need to find the area. And what is the area? Area is the diameter into the length. So because the total length is total length is small l. Okay, so total length is small l, and the diameter is your capital D. So because the force is going to be pressure into area, and the area is d into l. Okay, this area is d into l because the total length is small l and your internal diameter is small d. So d into l is going to be your entire area for this region. So that's why you will feel the force, right? Okay, so this is the force. I hope you have got this. Force is equals to pressure into area. In this case, pressure is P that is flowing through it, and d is the diameter of this wall. Internal diameter I have written here, internal diameter, and of course length is the length of this cylinder, that is denoted by small l. So, and I need to find the cross-sectional area that will resist the bursting. So this is called the bursting force, and equation of bursting force and the resisting force. So in case of the area of the cross-sectional area of the strip, that is, this is T, small t, and this is small l. So this is the area for this strip that will resist it. Okay, this is the cross sectional area on which the force is acting on. So the area of the strip is going to be l comma l into t, but l into t area is there here as well. I mean, you can see two red regions here, one is here and the other one is here. So both of them will resist it. So the total area will become 2 into L into T. So 2 into L into T, I have written it cross-sectional area. So now if you just calculate, L gets cancelled, you get PD over 2T. So this is the equation for your hoop stress. Delta H is equals to PD over 2T. Here pressure, P is pressure, D is internal diameter, and T is the thickness of the wall.